So here's the Pregel model. It's an internal project which is used within Google. It distributes vertices to processors or nodes in this diagram. Initialization, you partition the vertices across the processors, and then vertices uh, are given edges, so then they read edges, and then edges are given to the appropriate vertex. So vertex will get all the edges which outgo from that vertex, and each processor will have a whole bunch of vertices. And then vertices will exchange messages as per the Pregel program that is written for an application. The nodes will, some messages will be exchanged within a node itself when the destination vertex is within that node, and others will have to travel between nodes when the destination vertex is actually on another processor. This coordination of messages proceeds in what are called super steps. We'll come to that in the later chart. And so after all nodes have sort of delivered and received one round of messages, the master ensures that there is a synchronization across all processors, and then the next step proceeds. So everybody sends messages, then the messages get delivered, then again there does some computation. There's everybody sends messages, messages get delivered, and so on and so forth, until there are no more messages getting delivered. We'll see examples of algorithms implemented using this Pregel model in a bit. There are different implementations. Pregel itself is internal to Google, as we mentioned just a minute ago. Giraffe is an open source implementation of the Pregel model built on top of Hadoop, but there are essentially only mappers and no reducers, and all the message passing communication happens through remote procedure calls. Like Pregel itself, Giraffe distributes vertices across nodes. GPS is another implementation of the graph model based on the Pregel paradigm. It also distributes vertices across processors, but it also takes care of appropriately repartitioning the vertices between processors to make sure there is less communication between processors. So this is an important additional feature that GPS does for you, whereas in Giraffe you have to do anything like that yourself. GraphLab is yet another graph processing model, very similar from the programming perspective to Pregel in terms of every vertex is a program, but in here edges are distributed across nodes. So the information about a single vertex is actually distributed across processors. This is quite an interesting model. Obviously the architecture is very different from this one, because you're not distributing nodes to vertices to nodes, but edges. We won't go into the great details of the implementation architectures, but we'll look at a few applications of the Pregel model to some interesting problems. So here's the Pregel programming model. Just like we had the map-reduce programming model where you had to write a map function and a reduce function, here you have to write code for every vertex. Each vertex executes code once the graph is loaded, and the assumption is that the process of loading the graph makes sure that each vertex knows its outgoing edges. It may not have any idea about its incoming edges, but it knows its own outgoing edges. Vertices are distributed across processors, so each processor executes the code for all its vertices. So it does an update for every vertex that it has in what is called a super step. After the super step is completed, a second super step starts, and so on until the program halts, as we shall see in a minute. So each vertex first receives messages from all its in neighbors. So whoever is sending it messages on its incoming edges does some computation using these messages, and then decides to send some messages to its out neighbors possibly. After that, it decides whether or not to halt. What a halt means is that a vertex stays inactive once it's halted unless it receives a message from some other vertex in the future. If this does not happen and all vertices are halted, then the computation halts. So the master, as you mentioned in the previous chart, is responsible for making sure that the messages are sent and received from vertices, as well as checks whether or not all the vertices are in halt state. If they are, then it ends the computation. So let's do a couple of more examples using the Pregel programming model to solve a few important problems. A simple one is called max node. Essentially, given values across all the vertices, we would like to find out the maximum of these and make sure that every vertex at the end has the maximum value across all the vertices in the graph. So this is the simple program. You send your value along your outgoing edges and then start receiving values from incoming edges. For each incoming message, if you get a value which is greater than your value, then you replace yourself with that value and continue that and don't halt. But if you did not get any message which was greater than your value, then you halt. Let's see what happens if this is executed for every node. In the first step, what happens is that these are bidirectional edges, which I mentioned over here. So this means there's an edge from 3 to 6 as well as from 6 to 3. In the first step, 3 comes to 6. 6 doesn't do anything because it's already the maximum and it's never going to get a message greater than itself. But 3 becomes a 6, right? Similarly, 2 gets a message from 1, but it doesn't change because 1 is less than 2. But 1 gets 6, so it changes. So 6 and 2 did not change, and therefore they halt. So they are shown as shaded. These messages these vertices 1 and 4, however, are not halted, so they have to propagate their value in the next super step. So they are actually going to send the value on the outgoing edges. So so 1 sends its value to 6. 6 does nothing with it. 6 sends its value to 2, which now wakes up because it was sleeping, it was halted, but it got an incoming message, so it wakes up in the next super step and checks that yes, it did get a new value, so it becomes 6, and then it sends its value out to its outgoing edges, which doesn't do anything over there. So at the end, all the vertices are still halted. The computation ends, and as you can see, all the vertices have the maximum value 6.